Hello, everyone. This is our last lesson of new content. It's a good one, so I hope you enjoy. All right, let's dive in. Please try the warm-up. Pause the screen for a second. All right, let's dive in on how to do these. All right, so what is the z-score of a jump of 5 meters? So here we're just converting to a z-score. We're using our z equation. Remember, score minus mean divided by standard deviation. I got that. So that means you're 0.47 standard deviations above the mean. So a bit better than the average. Next, the probability x is less than or equal to 5. Probability x is less than or equal to 5. Remember, that's the same as less than 5 because for continuous things, measurements, the probability of it equaling is 0. This is the same as integrating the curve. You just the curve integrated between these bounds, or you can also do CDF, the normal CDF on your home screen. Some really low bound, your upper bound, your mean, and your standard deviation. Any of those will give you the right answer. All right, and then when you do any of those, whichever approach you do, you should get 0.682. Okay, next, if 50 people were to attempt to jump, how many would you expect to be between 6 and 7 meters? So we have 50 people jumping, and we're going to multiply that by the probability of someone jumping between 6 and 7 meters. So just 50 times, couple ways to calculate this. For this example, I'll use normal CDF. Again, lower bound, upper bound, mean, standard deviation. I got this probability, and then when you multiply those together, we'd expect about 4.76 people of the 50 to be able to jump that distance. All right, part D, what distance must an athlete jump in order to be in the top 1% of the population? So top 1%, well, that correlates to the score of 99% or the 99th percentile. So if we want to find that distance here, we use the inverse normal. Remember, that's how we go backwards to solve for these values of our probability that we want, our mean, our standard deviation, and here we get 8.52 meters to be in the top 1%. That's what you'd have to jump. All right, let's move on. Okay, so just real briefly, this is what we were looking at last time. I hope you remember this. The big tool, and you just did it on the warm-up, is using the inverse operation or inverse equation to solve for values inside of here to find actual scores. We're doing a continuation of that today. Okay, so the standard normal function, remember that's the huge equation. I don't have it queued up right here, but that's the big equation. Its parameters, that's standard deviation, that's a score, that's a mean, bounds. Those are all things that go into that big equation, the normal PDF equation. Okay, so here looking at the normal CDF equation with a range here. Remember, we have a lower bound, an upper bound, a mean, a standard deviation, and this all equals some probability. So this has 1, 2, 3, 4, 5 potential inputs and outputs that can go in here. So the question is, what ones can we solve for so far? What have we done? Most of our work was finding the probability. Recently with quantiles or k-values, we can solve for these two scores. So now what's next? Well, we need to solve for the mean and standard deviation given some other information. Also recapping, so x, the random variable x, is distributed normally with a mean and standard deviation. And remember for z's, these are distributed normally with a mean of 0 and a standard deviation of 1. Okay, let's dive in. How do you solve for mean? How do you solve for standard deviation? Sorry, this is a continuation of the inverse probabilities, which are these k-values. Okay, let me actually just dive right into an example here. So an adult scallop population is known to be normally distributed with a standard deviation of this. Notice they don't give us the mean. 15% of the scallops weigh less than some weight. Find the mean weight. So to start off with, so here's what's given. We know we have a normal distribution. We don't know a mean. We do know a standard deviation. We also know a score and the associated probability. Score, associated probability. Okay, very first thing, the biggest takeaway from this entire lesson is convert your probabilities to a z-score. And that's what this previous slide said but I wanted to let you see it through the example. You need to convert this probability to its associated z-score. What's a z-score that's associated with 15%? Okay, so I'm doing, you can do the inverse normal, 15%, 0.15, 0, 1. Remember, that's always for z, the mean, always the standard deviation. And tells me that the z-score is that. Okay, so now that I have a z-score, look what we can do. We can plug into the z equation. We know this value. We know a score. We know the standard deviation, and we're just left with our mean. So again, I plugged in the z value. I plugged in the score that was associated with that z value. I plugged in the standard deviation. Do a little bit of algebra, solve for your mean, and you will get the mean is 64.315. Again, that big step is convert the probability to a z-score. Let's look at another example. You're welcome to give this a shot and pause, or we can hang out and we'll do it together. Okay. Just briefly. So here, find the mean and the standard deviation. There's two unknowns. We do know it's normally distributed. We know a score and a probability, a score and a probability. So let's look at this, what this is saying over here. Again, we know it's normal. We need to find both of these. Just looking at the picture, because the picture might help us see this. Here it told us there's a 10% chance of being below 20, and there's a 15% chance of being above 29. That's what we know so far. So first off, I just wrote these. We have a 10% chance of being below 20. If I would need to convert this to z, what is the z-score associated with that? Inverse normal, and I get that this is the z-score for 10% is negative 1.28. Okay, now over here I'm looking for, so here know the probability of x being greater than 29 is 15%. Well, big watch out for your inverse normal. When they built that function in your calculator, they only built it for less than, not greater than. So you have to convert this to a less than. So if we want the upper 15%, well, in a less than idea, that is the bottom 85%. 1 minus 15, you get 85. So I put an 85 here, 0 and 1, and I get that that's associated with the z-score of this. Let's move on. We have two z values now. Now that we have the two z values, ask yourself, what do you think we can do? Well, now we're going to make a system of equations. Plug in to our z equation, the z equals the score minus the mean over standard deviation. The other z, the z equals the score minus the mean over standard deviation. Go through and solve this sucker. Just multiply both sides by sigma, and then divided those out to get these two equations. I have them both equaling sigma now. Now I can just graph this. I can just graph this as these are the y's, and these are the x's. So y's, x's, graph those, and here's what I got. I got this coordinate for the intersection. The way I built my function, my input is the first output, or my input here, so it comes first. So we see our mean is 24.97, and then standard deviation, these are kind of like the y's, is this one. So there you get the mean and the standard deviation via kind of system of equations. But to do that, they had to be able to show us both ends. We really needed both pieces of information. Okay, I hope that made sense. This is the kind of thing I'd really prefer to go slow on and check in with you guys. We don't have that luxury. Again, the big takeaway is back what this slide was saying. If we're given a probability and a score, you must convert to a z-score to find the mean or the standard deviation. In your practice tests, I know there's a couple questions like this. I'm not sure if you've seen it yet, but those are coming. Okay, let's practice this a little bit with these 6 questions. All right, and there are those questions. If you want to pause it, give these a shot. As always, don't hesitate to shoot me an email. We can talk on any of the video stuff or by email. I would love to help you with any of these ideas. That's what we're here for. All right, guys, take care. I hope things are going well for you, and I hope to talk to you soon.